beginning of everything, the Big Bang. The idea that the universe was suddenly born and it's not infinite. After the middle of the 20th century, most scientists thought of the universe as infinite and ageless. Until Einstein's theory of relativity gave us a better understanding of gravity. And Edwin Hubble discovered that galaxies are moving apart from one another in a way that fits previous prediction. In 1964, by accident cosmic background radiation was discovered a relic of the early universe, which together with other observational evidence made the Big Bang the accepted theory in science. Since then, improved technology like Hubble telescope has given us a pretty good picture of the Big Bang and the structure of the cosmos. Recent observations even seems to suggest that the explosion of the universe is accelerating. But how did this Big Bang work? How can something come from nothing? Let's explore what we know. We can ignore the beginning part of now. First of all, the Big Bang was not an explosion. It was all space, stretching everywhere, although at once. The universe started very small and quickly expanded to the size of a football. The universe did expand into anything space was just expanding into itself. The universe cannot expand into anything because the universe has no borders. There is by definition no outside. The universe is all there is. In the hot dense environment, energy must withstand itself with particles that extend only for the tiny slips of the time. From lone pairs of quarks were created which destroy one another, perhaps after giving off more glows. This spawned another short-living quarks to interact with forming new quark pairs in clones again. Matter and energy were not just theoretically equivalent, it was so hot they were practically the same stuff. Somewhere around this time matter won over antimatter. Today, we're left with almost all matter and nearly no antimatter at all. Somehow, 1 billion and 1 matter particles were formed for every 1 billion particles of antimatter. Instead of one massive ultimate force in the universe, were now several refined versions of acting under different rules. By now, the universe has stretching to the billion kilometers in diameter, which leads to the decrease in temperature. The cycle of quarks being born and converted back to the energy suddenly stopped. From now on, we work with what we have. Quarks begin forming new particle hadrons like protons and neutrons. There are many combinations of quarks that can form all sorts of hadron, but only very few are reasonably stable for any length of time. Let's take a moment to appreciate that by now only 1 second has passed since the beginning of everything. The universe, which has grown to 100 billion kilometers, is now cold enough to allow most of the neutrons to decay into protons and from the first atom hydrogen. Imagine the universe at this point as an extremely hot soup, 10 billion degrees Celsius filled with the countless particles and energy. Over the next few minutes, things cool and settle down very fast. Atoms form out of the hadrons and electrons, making for stable and electrically neutral environment. Some call this period the Dark Age because there were no stars, and the hydrogen gas did allow visible light to move around. But what's the meaning of visible light? Anyway, when there's nothing alive yet that could have eyes, when the hydrogen has clumped together after millions of years, and gravity put it under great pressure stars and galaxy began to form. The radiational dissolved the stable hydrogen gas into plasma that still frames the universe today and allow visible light to tap us. Finally, there was light. Okay, but what about the part we did talk about? What happened right at the beginning? This part can be defined as the Big Bang. We don't know at all what happened here. At this point, our tools break down. Natural law stop making sense. Time itself becomes wibbly-wobbly. To understand what happened here, we need a theory that unfolds. Einstein, relativity, and quantum mechanics. Something complex scientists are working on right now. But this leaves us with lots of unanswered questions. Were there universe before our own? Is this the first and only universe? What started the Big Bang, or did it just occur naturally based on laws we don't understand yet? We don't know, and maybe we never will, but what we don't know is that the universe as we know it started here and gave birth of particles, galaxies, stars, and Earth. And you things we observe are made of dead stars. We are not separate from the universe. We are part of it. You could even say that we are the universe way of experiencing itself. So let's keep on experiencing it until there are no more questions to ask.
Let's start with some absolutes that we need to accept. 1. There is no such thing as absolute motion or absolute rest. Objects move relative to each other. For example, look at the track with two kids playing catch. The track is moving at a constant speed of 50 miles per hour, but as the kids are also moving with it, they could easily think they are standing still. When the children show the ball at 10 miles per hour, they observe that the ball they have shown is moving at 10 miles per hour. But their little brother who is not on the track and is standing still has observed that the ball has moved at 60 miles per hour. He has added both the speed of the track and the speed of the ball together. But is the little brother really standing still? No. The earth is constantly in motion, the sun is constantly in motion, and the galaxy is constantly in motion. Therefore, nothing is ever at absolute rest or absolute motion. Things just move relative to each other. This is called classical relativity. The second thing we need to accept is that the speed of light is the same for all observers. So let's imagine a beam of light being reflected between two mirrors. Let's replicate this setup so we have another beam of light being reflected between another set of mirrors. But this time, the mirrors are moving close to the speed of light. We can see in the moving set of mirrors that the beam of light is moving at a greater distance. Now, let's put a couple of people in this scenario. Meet Alex. He sits inside the moving set of mirrors and Bill sits inside the stationary set of mirrors. The speed of light must be the same for both Alex and Bill, and their light beams must hit the bottom mirror after the same amount of time has passed. But as Alex's light beam is covering a longer distance, how is that possible? Well, the only way for that to work is if time for Alex slows down. Time for Alex has slowed, which allows his light beam to travel a greater distance. Look at it this way. Speed equals to distance divided by time. As Alex's distance is more, the value of his time must be more, or rather, Alex's 1 minute actually turns out to be longer than Bill's 1 minute when you compare the two. Time has slowed for Alex. This is called time dilation. In the previous section, we spoke about how the speed of light remains the same for Alex and Bill because while the distance of Alex's light beam travels more, his time has dilated. However, distance and time don't increase by the exact same amount. In fact, time doesn't actually dilate enough to account for the speed to remaining the same for both boys. Something else happens. Length contraction. When objects are moving close to the speed of light, not only does time slow down, but the object itself contracts. This is called length contraction. So, in this scenario, Alex and his mirrors are actually smaller than we thought, and therefore, the distance and the light beam has to travel in is actually smaller than we thought. In conclusion, time dilation and length contraction work together to ensure that the speed of light remains the same for both Alex and Bill.
Time slows down for objects traveling close to the speed of light, and time stops altogether for objects traveling at the speed of light. It then follows that time must go backward if objects travel faster than speed of light. So far, it has been seen that no object can travel at the speed of light. When approaching the speed of light, objects start to increase in mass rather than speed, and it will take an infinite amount of energy for an object to achieve the speed of light. This is why we cannot travel back in time. We have simply not be able to reach a greater speed than the speed of light. Einstein realized that the special theory of relativity, which we explained previously, only worked for circumstances when things move at constant speed through the universe. What about when objects speed up? What about the effect of gravity? And come to think of it, what is gravitational pull after all? Einstein theorized that objects warp space-time around them, causing it to become curved, and as a result, objects experience gravitational attraction to each other. This warping of space-time explains how objects behave as they move through space. This is the general theory of relativity. Well, countless experiments had been carried out and Einstein's equation hold true. Modern GPS uses Einstein's theory of relativity to pinpoint our location with impressive accuracy. In 1971, an experiment was conducted with 4 super-accurate atomic clocks where were set to the exact same time as the reference clock. The clock were placed aboard commercial flights and the planes flew twice around the world, first eastward and then westward. When the clock returned and we compared to the reference clock, the clocks were no longer synchronized and the difference was consistent with the prediction of special and general relativity.